what we're looking at here is we want to apply what we know about derivatives to other situations. It's kind of natural to think about velocity and acceleration in terms of motion. I mean, that's the most, common application of those. However, as you can see here, if we recognize derivative as a rate of change, we can really think of anything that we're able to model and look at the rate of change for whatever that is, okay? We can model costs of things, okay? Depending on different variables, the price of different components that are put together to make it, the price of labor, the price of shipping, advertising, all that kind of stuff. People do a lot of research and all that kind of stuff into coming up with how much is this thing actually going to cost to produce. All right. And obviously along with that, it's not listed here, but you could talk about, your profits then. If you know your costs, you can then look at your revenue minus your costs and you can determine your profits, okay? But also things like area. If something is growing or shrinking in area, you actually could model that and we could figure out a rate of change for the area. A population of a city, you look at a velocity, what you're looking at is the change in population. And then also volume. If you're blowing up a balloon, how quickly is that balloon getting bigger or increasing in volume? That's how you deal with flow rates or things like that. If we were doing AP Calc and going more in depth, we would actually do implicit differentiation, which is really kind of cool. A related rates problem. You might have heard some in calculus bemoaning that because it can get tricky. But if we know that, let's say we're emptying something and we measure and it's emptying a gallon every 10 seconds or something, that's a rate, and then we can actually apply that to other things and figure out, okay, well, if it's dumping out that much volume, how fast is the level of the water coming down? So some pretty cool stuff. Now, some terms that you need to be kind of familiar with is a marginal cost, okay? The marginal cost is the rate of change in cost. And you might think, well, how in the world does a cost change? Think about that. How would the cost of making something change?
If you're producing more.
Okay, if you're producing more, why would the cost change? And of course, we're talking about the cost per unit. Why would the cost per unit change if we're producing more of them?
To buy more stuff. It's taking less energy to produce them. You produce more at the same time.
Okay, you can buy more stuff. If you just keep everything running and produce more all at once, then yeah, it takes less time overall.
You need to pay taxes for having for the space where you're manufacturing in, and no matter how much you're manufacturing, you're gonna pay the same amount.
Okay, there are certain fixed costs that stay the same no matter how much you produce. Like the lights are on, it doesn't matter, and schools do this too. My father's an accountant, and one of the things he did with companies was help them figure out, how much would it cost to do this or that. And actually with my old school, he met with the administration and stuff and helped them figure out what's the cost of adding one student. Just the bare bones cost. If we put one more student in a classroom, how much is that actually going to cost the school? And then that enabled them to figure out what kind of scholarships they could give. And still at least break even, cover their costs and that sort of thing. So figuring that sort of stuff out, there are certain fixed costs. We have the lights on whether there's 22 of you in here or 5 of you in here. So that's not going to change. So good. There's a lot of different things that can change the cost. Does making more always cost less?
No.
Why not?
More space.
Okay, you might have to pay more workers.
More space, you mean you have more land or something.
Okay, we might have to upgrade our facilities, get bigger facilities or something like that.
You need more materials to produce the stuff from.
Okay, and in general, the more materials you buy, you get a lower price. But what if you're reaching the point where they're now becoming scarce? You know, supply and demand, the price could start going up. Okay, or your choice of vendors who can actually provide that much of the resource goes, you know, your choices are limited and their prices go up. Or with the workers, now you're having to pay people overtime, so the price is going up. So the challenge of a business or a manufacturer is finding that happy medium where we can produce enough to minimize the cost, but we're not now having to do all this extra stuff that makes us pay more. That's why for some businesses, they choose not to grow. You know, they choose, they're happy with the profits they're making, or they're happy with their status there, and they choose not to expand. And actually what usually ends up happening is then they're able to actually charge a little bit more for their product because they just increase demand by not producing more. Okay? So that's one thing, but that rate of change, how quickly is our price going up or down, depending on, or our cost going up or down, depending on how much we're producing. Area, okay? This one is kind of obvious, but population growth rate. If we have a function that can model, you know, our population, and it doesn't have to be population like of a city. This could be the population of bacteria, okay, or something like that. We could figure out, okay, this is the model, there's an exponential growth model, we know this bacteria reproduces at this certain rate. We can figure out how quickly it's going to spread, or things like that, okay? And then likewise, volume is another one that's kind of obvious. How quickly is something getting bigger in the amount of space it's taking up, or smaller even, okay? So there's a couple of things there, and I wanted to run through a couple examples here. One, looking at marginal cost, and kind of seeing what the types of questions that we could ask are, how those would be phrased mathematically, and then what strategies we would use mathematically to figure that out, okay? So here's a case where we're producing X, which is the number of items in this factory, and the cost is given by this equation. They figured out, and this is how these big models come out, they have those fixed costs. It's $2,200 a day in fixed costs. They have the raw materials to purchase the stuff in order to make these items, and then they have the labor, okay? And they were able to calculate that in terms of how much are they paying per unit in labor. And they add all that up together and come up with this cost function. All right? So, let's think about these one at a time here. Find C prime of X, and this is our marginal cost function. So this is going to be a function of the number of items we're producing. We multiply this, or use our derivative rules, 0.0039 x squared plus 0.004 x plus 5. There's our marginal cost function. Okay?
The fact that we dismiss the constant makes so much sense at this point.
Mm-hmm. Yeah, because this isn't going to change at all. Yeah, that's a good observation. Now, part B, what are they really asking us to do? Find the marginal cost when 150 items are produced.
Again, 150 for X.
Yeah, that's all we're doing. We're doing C prime of 150. Okay? So let's figure that out.
It's 14.375.
14.375. Okay. So what others you guys got?
Yeah.
Alright. Good. Okay, so what does that mean?
Well, you would have to round up, so it'd be $14.38.
Okay. So $14.38
To produce 150 items.
150 items produced, like ignoring the fixed cost.
is that what that means?
Oh, it's a rate of change. No, it's not a rate of change.
The cost
It is a rate of
It is a rate
change.
of change.
Cost is increasing by $14.38 an hour.
Well, no, per item. Per item. So this is, if we're producing 150 items, then our cost per item will be $14.38. Where the rate of change comes in is our overall costs are going to increase $14.38 per item. Okay, so that times 150, that's how much it increased.
So
Okay,
that's what your cost per item.
per item, yes.
So if you plug it into the original equation, what would you get? The total cost for everything?
That would be the total costs for production for the whole day.
Okay.
Okay. So it's that per item, yeah, and C of 150. Now, here's the thing: we wouldn't plug 1438.
She's
And,
over there, right? She's in the
oh, Miss Lennox room. I think she's covering it for her. We wouldn't plug in the 1438. We're plugging in the 150 to the original cost function. That would give us our total cost, okay, for the day. Now, if we do part C, okay, find C of 151 minus C of 150, okay? Let's see what happens here, all right? So notice we're using the original function. You need to be able to see it, okay? Use the original function. So do it once, plug in 151. Once you get it, let me know what you got.
Thank you. Have a good day.
3,448. Okay. And then if you plug in 150,
3,433.75.
3,140.
Oh, 400. 433.
0.75, you said?
Yeah.
Okay. So what do you get when you subtract those?
I'm guessing 14.38.
14.44.
Okay. 14.44. So, what do you think?
They both give you the cost of producing one item, roughly.
Okay. What's the difference in these two results?
and B gives you how much item, like one of the items, one of 150 items is gonna cost, and number C gives you how much 151st item is gonna cost, or no?
Almost. We're on the right track, because if we plugged in C prime of 151, it wouldn't exactly be, it would actually be 1449. Okay? Actually did that one. C prime of 151 is actually 1449.6, so we'll call that 1450 per item.
I don't know.
Well, look at that number compared to what we got for B compared to what we got for C. And that might tip you off.
6.
There's a 6 cents difference, right? From one to the
Yes.
other to the other. So what is C?
The middle.
It's the middle, it's the average, right?
Oh.
Remember we talked about instantaneous velocity versus average velocity? Okay? The average, if we're using 2 points like this,
It's the average.
we're finding an average velocity. Okay? Here we found the instantaneous rate of change at 150. Here's the instantaneous rate of change at 151. Okay? But the average velocity was halfway between those two. Okay? So, hey, interesting to look at these together here. But this would be our marginal cost. It's the cost of each item when we produce 150. So, in order to get a profit, in order to sell these for a profit, we got to charge more than $14.38. Okay? Now, notice here too, it costs more. We're actually past that min value where we're minimizing our costs. We're producing more because notice the price is now going up the more we produce. You notice here our marginal cost is parabolic. All right? The price per item is parabolic. So we want this, ideally.
So we're past that.
So we must be 150 and 151 must be on that upswing. Okay? Now, if we found the vertex of this parabola, we would be able to figure out exactly what that x would have to be to minimize our cost per item.
You just do like B over 2A, whatever that formula is.
Or you just make it equal to zero.
Negative b over 2a?
Yeah.
Yeah, you could do that with that marginal cost. That'll minimize the cost per item, which in turn will minimize our overall cost because the other fixed costs that won't be impacted regardless. So,
Thank you.
all right. So, any questions about this one? An interesting study there. All right, let's look at one other one here. Okay, we're looking at a change in area. How quickly is this triangle growing in area as our angle theta changes? Okay, so we have this triangle, you know, the ends are connected evidently, and one side's 12 and one side's 10, and we're pulling it open, okay? So the angle is what's changing. These two arms aren't changing at all, AB and AC,
B and C has to change.
okay? BC will change, and our area will change, okay? So in fact, we could do one where to determine how quickly BC will be growing. Okay, that one's a little more complicated because we have to use our law of cosines and take a derivative of that mess. But in this case, though, we have to think about area, okay? Now, what's our formula for the area of a triangle?
Base,
Half
base, base,
base.
1/2 base times height. Is that going to help us here? No.
There's another formula, isn't there?
But there's a variation on this formula. Do you remember what that one was that involved the angle?
Something with a sine.
Yeah. It involves sine of theta. Remember, it was, if you had side angle side, it was 1/2 times the length of one side times the length of the other side times the sine of the angle in between. Okay? So 1/2 times 12 times 10 times the sine of theta. Okay? And that actually goes back to 1/2 base times height. If I drop the height here, okay, I could figure out height by taking sine of theta equals h over 12, opposite over hypotenuse. And then 10 would be the base of my triangle, and the height of my triangle would be 12 times the sine of theta. Okay? You remember deriving that last year at all? Yeah, and we're just going to substitute it in right here for h. Okay? So now we have this, so it's 60 sine theta equals our area. Okay? So how do we figure out our solution here?
So it says things at 60 degrees.
Okay, we want it when it's 60 degrees. Okay, now sine of 60 is root 3 over 2, so the area will equal 60 root 3 over 2, which is 30 root 3 centimeters squared. But that's not what we asked. It's saying find the rate of change, not just what the area
So it's a
is.
derivative.
You have to find the derivative of the area.
That's right. We've got to find the derivative of the area with respect to theta.
So we get the derivative of 60 sine.
60 cosine.
Yeah.
So yeah, so 60.
So it's just 60 cosine.
What room is she in?
Actually, you can just put it on her desk.
No, I need to ask you a question.
Oh. 322, I think.
So then we won't have to.
So yeah, cosine of 60. Okay, in terms of theta, it's 60 cosine theta, and then you plug in 60. 60 cosine of 60.
61. Okay.
Cosine of 60 is 1/2. So 60 times 1/2,
30.
30. And then what would our units of measure be here?
Centimeter.
Degrees for.
2 centimeters.
It's the same.
Look at our derivative. Area is on top.
Centimeters per degree.
It'd be centimeters squared per degree. Centimeters squared per degree. That would be our unit of measure. Okay? Now, obviously, that's only at that moment. When you change the angle to something different, the rate of change is going to change as well. Okay? So, and you guys know too that, you know, as you rotate up, cosine is going to get bigger and bigger and bigger until, or I'm sorry, cosine is, sine is getting bigger and bigger until you hit 90. Okay? So our area is going to be growing, right? But then once you pass 90, sine starts going back towards 0. So as you make it an obtuse triangle, your area is actually going to be getting smaller. Okay? So. Alright, so we can apply rates of change to all kinds of different stuff. And paying attention to your units of measure, and how all that works is going to be really important, okay? But look back at your derivative. That'll kind of tip you off. What was our area measured in? Square centimeters. And then the angles were measured in degrees. So it's square centimeters per degree. Likewise back here, we're taking the derivative, instead of writing it this way, we could have written it as the derivative of the cost with respect to our x. Okay, so what was cost measured in? Dollars. And x was the number of items, so that's why it's dollars per item. Okay, so. Alright, so there's a little bit of practice, some various applications. Here we have water draining from a swimming pool. Okay. By the way, notice sometimes like here on A and B, they're asking for an average rate versus an instantaneous rate. Alright, so just be careful with the language there. Okay? So that's all I have, and we'll use the rest of the time we can get started.